class activity sheet number 1, section 4, which is looking at the answers for oxidation reduction. And remember when we do this section that we're going to follow the rules that I gave in class on Wednesday, and here they are. I'm just going to copy and paste them from the lecture notes over here so we know what we're doing. Okay, so these are the rules we're going to follow. Neutral element, just elemental state, standard or elemental state. Then oxidation number is 0. For any ion, the oxidation number is the charge of the ion. And the sum of oxidation numbers in any molecule or polyatomic ion must equal the total overall charge. So if it's a molecule, the total overall charge is 0. On polyatomic ion is the charge of the polyatomic ion. And then finally, for covalent compounds, we're going to go in this order. Oh, goodness, I went opposite. This should be fluorine is -1 and then oxygen is -2. Should swap those. That's not going to affect you guys in the test because I don't think I ask you one with oxygen and fluorine, but let's see, where's my little guy? There it is. So these two should be swapped. I apologize. Okay, so if we follow these, then in the first case, we've got H2 and Cl2. What's the oxidation number on hydrogen here? Perfect, it's 0 because it's elemental hydrogen. Okay, what about chlorine? Perfect. Elemental chlorine. Okay, here's HCl. So this is a covalent compound because that's 2 nonmetals. So we're going to follow the rules in order. So do I have an H? That's the first one listed. Yes, I do. So therefore the charge or oxidation number, rather, on the H is +1, according to our rules. And since the overall sum of oxidation numbers has to equal the charge, then we know that the oxidation number on chlorine is -1. Perfect. Okay, so then what was oxidized and what was reduced? Actually, we have to remember what oxidation and reduction is. I'm going to write this on the side. It'll help me do this. So oxidation, let's see here. Oxidation. Oh goodness, I shouldn't try to draw sideways. I should just draw it down and make it small. So oxidation is losing electrons, where reduction is gaining electrons. Okay. And one way to remember that is oil rig. Oxidation is losing, reduction is gaining electrons. So, but remember, electrons have a negative charge. So if I'm going from a 0 to a negative charge, then I must be, oh here, I must be gaining electrons. And if I'm going from 0 to a positive charge, then I must be losing electrons. So here we see that since oxygen becomes more negative, then it must have gained electrons, so that would be reduction. And you guys are exactly right. The hydrogen must have been oxidized. Remember, you'll always have both of these going on, because if you're losing electrons, they're going somewhere, and if you're gaining electrons, they're coming from somewhere. And so as a result, you'll always have both of them at the same. That's exactly right, Trisha. That's a really good way to remember reduction, because that way you don't have to be confused about the electrons are negative, but I'm gaining, but that's reducing. But yeah, reducing the charge is reduction, and that's it. Okay, good. Let's try chromium and oxygen here. So the oxidation number on chromium is 0. Oxidation number on oxygen here is 0. Oxidation number, oxidation number here, this is an ionic compound, so the oxidation number will be the same as the charge. But because chromium is a transition metal, we're going to have to deduce the charge the way that we used to do in chapter 4. So what do we know about this compound? Oxygen is -2. On an ionic compound, oxygen will always be -2. So since there are 3 oxygen atoms and they are each -2, that's going to give us a total negative charge contribution of -6, which must be balanced out by the positives. So total charge contribution from the positive ions of +6, there are 2 chromium, so each one must be, as Jeff and Christy noted, +3. Perfect. So the oxidation number of chromium then is +3, and the oxidation number of oxygen is -2. So which one was oxidized and which one was reduced? Oxygen was reduced. The charge went down. It became more negative, so it must have gained electrons, so this was reduced. And the chromium then was oxidized. Okay. Anybody know why it's called oxidation? It's because it turns out oxygen is a really good oxidizing agent. And an oxidizing agent does what? It reduces, yes. An oxidizing agent is something that was reduced, but in the process of being reduced, it helps something else be oxidized. That's why it's an oxidizing agent. The agent helps something else be oxidized. So oxygen is very good at helping other things lose electrons. And so it is a very good oxidizing agent. So this is kind of where oxidation, it does come from the term oxygen. So what was oxidized must have been the reducing agent. It helped something else be reduced. You guys remember this in class on Wednesday? That the thing which was oxidized was reducing agent, and the thing which was reduced is the oxidizing agent. Okay, let's try this one. Mercury 2 oxide decomposes to form mercury and oxygen. So what is the oxidation number of the mercury and the oxygen in this compound? Beautiful. Jeff recognized that the oxygen must have been -2 since this is an ionic compound, and therefore the mercury must have been +2. Okay. On the right-hand side, what's the oxidation number of this mercury? Perfect. And this oxygen? Perfect. Okay, so the mercury goes from +2 to 0, and the oxygen went from -2 to 0. So what was oxidized and what was reduced? Uh-oh. Trisha and Jeff, talk to each other. Or look at it again. Jeff says he's wrong. That's correct. The mercury was reduced. See how the charge went down? It gained more negative charges to go from +2 to 0, so it was reduced. And the oxygen in this case was oxidized. Jeff was fooled by the fact that it seems like oxygen is often the one that is reduced, but it's not. Okay, so mercury was reduced, so in this case it was the oxidizing agent, and oxygen was oxidized, so that in this case it is the reducing agent. Okay, I don't want to necessarily do all of these. Let's do some of these ones with covalent compounds because those seem a little trickier. Okay. No, not necessarily. I just wanted to remind you of that particular key, Jeff, that we've got the thing that is reduced is the oxidizing agent and vice versa, because I think there's a question like that on the test. And it's just something you'll see around, so it's really good to familiarize with yourself with it because it is very, very easy to forget, and it certainly seems backwards to me. I don't know if it seems backwards to you. I can only assume. Yes, you should You should memorize the blue rules. But really, Tricia, what you learned from the blue rules is that an oxidizing number is pretty much the same thing as a charge if I am an ion. And this is the only thing that's kind of different and new, because here it's where we're looking at covalent compounds and treating them as though they have a charge. So this is, if you just remember for steps 1 through 3, oxidation number is the same thing as the charge, and then memorize step 4, you should be good. But let's do these last 3. We did the first 3 in this section. Let's do the last 3 in this section because they have covalent compounds. We can work through that. So for carbon monoxide plus oxygen goes to form carbon dioxide. Let's look at carbon monoxide. This is a covalent compound, so we're going to follow the rules. Is there a hydrogen? No, there's not. So next, is there fluorine? No, there's not. Yeah, Tricia, there are different versions of the solubility rules. I tried to simplify them in my lecture notes so that there were just 3, but yeah, the solubility rules generally all say the same thing. So whichever one you find that's easiest to remember is just fine. Anyways, okay, so Jeff, you tell me. Well, thank you. I tried to make them simpler, but still say the same thing. Christy's right. Oxygen here is -2, which means that the carbon here must be what? +2, exactly. There's only 1 carbon and 1 oxygen. Total charge of that thing is 0, so it must be equal and opposite. What's the oxidation number on this oxygen atom here? 0, because it's elemental. Perfect. All right, now I've got carbon dioxide. And again, okay, covalent compounds. I don't have a hydrogen, I don't have a fluorine, but I do have an oxygen, and the oxygen is -2. Perfect. All right, so which means then, since I have 2 oxygen atoms each with a oxidation number of -2, then the carbon must be +4. Perfect, Tricia. Okay, so then we look at what changed to determine what was oxidized, what was reduced. So what changed? Okay. The O, this O in particular, went from 0, and here it's at -2. Notice I've got 2 sets of oxygen on the left-hand side. So not every oxygen atom in this reaction was reduced, right? Some of them stayed the same, but some of them were reduced. So oxygen, we will say, was reduced. And then, as Jeff noted, carbon was oxidized. It went from +2 to +4, so it must have lost electrons because it became more positive, so that this was oxidized. That was it. Okay, and if this one didn't change, then you don't worry about it. It's not that every atom is going to be changing. It doesn't. You just look at the ones that do change, and that's all you need to do. Okay, let's look at this one. We have hydrogen peroxide decomposes to form water and oxygen. So if we break this apart following the rules, okay, the rules say for covalent compounds, H is always +1. So if H is +1 and there are 2 of them, then what does oxygen need to be so that your oxidation numbers will balance out? There are 2 oxygen atoms. Teresa says -1. Exactly right. You guys are exactly right. Does that bother you? Good. It should bother you a little, and that's okay. It's okay to look at that and say, gosh, I'm used to seeing oxygen be -2. This is a little bit bothersome. But could you possibly make oxygen here -2 and still have a neutral compound? Yeah, like it would never work, right? So that's why, obviously, these aren't charges, they're oxidation numbers. But that might also explain to you a little bit why maybe this compound isn't very stable. Hydrogen peroxide will spontaneously decompose according to this reaction when exposed to light, which is why when you buy hydrogen peroxide from the store, they sell it in brown bottles so that it helps slow down this decomposition reaction. So there you go, something new. All right, so hydrogen here is +1, therefore the oxygen must be -1 according to our rule here that says, well, the sum of the oxidation number is going to be the charge. Since hydrogen has to be +1, oxygen has to be -1. And hopefully you see why we're going to go in order, right? Because the hydrogen must be +1, because it gets higher priority, that's what determined that the oxygen had to be -1. Okay, so then on the right-hand side for water, again, this is a covalent compound, and here hydrogen is +1, and there are 2 of them, so this oxygen atom must be -2, perfect. Jeff says, if they're the same number of subscript, will you go with the first element? If they are the same number of subscript, then they've got to have equal and opposite charges, like they were here, right? Both 2 ones, 2 ones. Here I went with the first one only because the rule said, look at hydrogen first. If there's not hydrogen, then you can say the oxygen's -2. But if there is a hydrogen, then it has to be +1. Good. All right, and then here on the far right, we have oxygen. What's the oxidation number of oxygen here? 0. That's right. Yeah, the hydrogen is listed. Well, you could say it's listed first because it's positive, because we always put the cation first and the anion first. But remember, Tricia, that these are not ionic compounds. And so we're not really following those rules anymore, because the rules for having the positive ion first and the negative ion second only is for ionic compounds. Covalent compounds will often show the central atom first, which is not the case in either of these. Okay, so you guys tell me what changed. Oxygen changed. Okay. What did it change from? What did it change to? It went from -1 to -2. That certainly looks like reduction. Okay, reduced. Okay, well, what was oxidized? It also went from -1 to 0. What? Can the same thing be reduced and oxidized? Yeah, that's what the numbers are telling us. That might also make us uncomfortable, but the fact of the matter is, if we assign numbers correctly, we don't even have to think. We just follow the numbers. We say -1 went to 0, -1 went to -2. This was reduced, and this must have then been oxidized. It's not the same oxygen atom which was reduced and oxidized. Oxidized. It's not the same oxygen atom. If we balance this equation, we'd probably have to put a 2 here to 2 here. And we would find that half of the oxygen atoms were reduced and half of the oxygen atoms were oxidized, right? So it's not this oxygen atom was both reduced and oxidized, but it's oxygen atoms in this compound. Some of them were reduced and some of them were oxidized. And the numbers told us that. Once we assigned our oxidation numbers, we could very clearly see where those changes were. Any questions on this one? It's a tricky question. Tricky triggers. What about the H? The H was +1 on the left-hand side, and it was +1 on the right-hand side. So it didn't change. It must not have been oxidized or reduced, because it did not appear to gain or lose any electrons because the charge didn't change. Aaron's got a great question. Why is it not necessary to balance the equation before assigning oxidation numbers? And the answer is that the oxidation numbers has to do with the ratio of atoms in the compound, as we did here and here when we were assigning those oxidation numbers, and doesn't have to necessarily do with the number of atoms that was used overall. You'll note, Aaron, that when trying to explain how many of these were reduced and how many of these were oxidized, then I had to balance it. But the truth was to say, in order to look at oxidation reduction, I could just say, well, clearly some of the oxygen atoms were oxidized and some were reduced, and I'm obviously not making any claim as to how many until I could balance it. Tracy says the answer sheet says it was oxidized. The hydrogen? No. If it does, it's wrong. And that's a terrible thing. I'm gonna look. I'm gonna believe you, but I'm like shocked that I would make such a silly error. Let me look at this. So here I am in Canvas. Just to remind you guys how to get here, course file box, in class activities, chapter 6 ICA key, and I can even just preview this here. Who wrote that darn answer sheet? The same person that said decombustion instead of decomposition. Apparently, maybe I wasn't feeling very well when I wrote this answer sheet. So, look at that. That's terrible. And I have the numbers perfectly correct. I mean, it's obvious from the numbers that hydrogen did nothing, but that oxygen was reduced and oxidized. Terrible. You should make a post on that, Tracy, in the Chapter 6 forums, just to warn everybody. Make sure that they know. Decombustion. Ridiculous. I'm ridiculous sometimes. Okay. All right, so let's do the last one, because the last one is extra fun. It takes it just one more step further. Okay, so now we've got an ionic compound, but this ionic compound contains a polyatomic ion, and polyatomic ions are held together with covalent bonds. So this is making us bring everything we know together in order to answer the question. So ionic compound, what is the charge on the sodium? +1, perfect. And the charge on the nitrate is -1, but I can't look at the whole nitrate. I have to look at each individual atom. Okay, but it will help me to know that the charge of the nitrate is -1. Because then I say, oh, these are covalent bonds. I'm going to go look at the rules. There are no hydrogen atoms. There are no fluorine atoms, but there is oxygen. What would the oxidation number of oxygen be inside of a covalent compound? -2, perfect. -2 for the oxygen. All right, now let's say there are 6 oxygen atoms and they each have an oxidation number of Let's say there are 3 oxygen atoms and they each have an oxidation number of -2, and that the overall polyatomic ion must contain a charge of -1, and we know that the sum of the oxidation numbers has to equal the charge. So whatever the oxidation number on nitrogen is, plus -6 has to equal -1. So the oxidation number on nitrogen must be +5. Does everybody follow how I did that? What I did there? Or another thing to do would be to say, we just look at this whole sodium nitrate as one whole compound and it's neutral. And since sodium is +1 and oxygen is -2, and there are 6 of them, we're going to say -6 plus 1 plus what is 0 to make it neutral. Just another way. Okay. Yes, Jeff, except those, yeah, it's got, yeah, -1. Okay, so let's do it on the right-hand side then. You guys tell me, in order, what is the oxidation number on the sodium, on the nitrogen, and on this oxygen? Like, oxidation number, comma, oxidation number, comma, oxidation number. Christy's exactly right. Jeff got a good start. Sodium is +1 still, because it's an ionic compound, and we know the charge on sodium in an ionic compound. Says the NO2 is held together with covalent bonds. We know that the oxygen is -2, And we know that the overall charge on the NO2 is -1 because we know the charge on the sodium is +1. Since the oxygen is -2 and there are 2 of them, and the nitrogen has to balance out all but a -1 charge, then the oxidation number on the nitrogen must be +3. All right, and then on the far right, what is the oxidation number on this oxygen atom? 0. Perfect. Okay, now you guys look at those and you tell me what changed. Okay, Aaron says nitrogen was reduced and oxygen was oxidized. So my nitrogen went from +5 to +3. Sure looks like the charge went down to me. It must have gained electrons, and that is reduction. Reduction. Okay. And this oxygen, now hang on a second, there's more than one oxygen, right? Some of the oxygens remain the same, and some of them then were oxidized. But we would say in this reaction that oxygen was the element that was oxidized, and reduction was the element that, or sorry, nitrogen was the element that was reduced. And if we really wanted to, and this isn't necessary, I'll never test you on this, we could balance the equation and say, for instance, that this many, let's see, I'd have to put a 2 here, a 2 here, and that would be perfect. That 2 of my oxygen atoms were oxidized, whereas 4 of them did not change, and then 2 of my nitrogen atoms were reduced. Do you guys follow? While we're doing homework, will we look at the previous section, right-hand second question? This one? Barium hydroxide plus sulfuric acid? Okay. Oh my. This is a good question. I like it. Okay. In this case, we've got 2 interesting things going on. So if we look at what's soluble and what's not soluble, barium hydroxide, this is a solid, right? Because it's not soluble. Sulfuric acid then is going to be soluble. This will be aqueous because sulfates are always soluble unless they are with barium, lead, or mercury. And then we look at this side and say, oh my goodness, here I've got barium with sulfate. Guess what? That makes it a solid. Because that's rule number 3 of the solubility rules. And then I've got water, which is a liquid. And if I came to you to look at the net ionic equation, the net ionic equation says like what changed, right? I would say everything changed. So the net ionic equation would probably look something like this. It would have my barium hydroxide, which was solid. And then this is aqueous, so it is ionic. So it does have individual ions. The answer key is wrong on this one too. Somehow I knew it would be before I even checked it. And that goes to form barium sulfate, which is also solid. Anything that's solid or liquid is going to remain in the net ionic equation. There's your key. And then anything that was aqueous but that made the things that were solid or liquid also remain in the net ionic equation. Thank you, Tracy. I am so sorry that this confused you. I guess the good news is if you saw that and you noticed it and were confused, then that means that you know what it should be, and that's a great sign. When you can correct me, that's awesome. But yeah, post about it so that anybody else who's confused or people who were not confused but maybe should be but don't know that they should be will be aware of that. Thank you, Tracy. Great question. Okay. Anything else on this in-class activity sheet before we move on to the next section?